Good morning. Till last class we have discussed single step methods to solve initial value problems, and we have reviewed some of the methods and then try to attempt some problems. So, in the single step methods what we have seen, to compute value at a particular grid point, we need one value at one past point. Okay. So, this is a single step method. Okay. So, that means to compute y of x n plus 1, we need y of x n. Okay. So, as the name suggests, in multi-step method, maybe we could expect that instead of one past point, we need several past points. Okay. So, further these multi-step methods can be classified into different varieties. So, let us look at into these multi-step methods. So, multi-step methods. Okay. So, what it does, this uses past values of y of x and or y dash of x to construct a polynomial that approximate the derivatives and extrapolates into the next interval. So, what it does? It uses past values of y x and or, that means could be sometimes y dash as well or sometimes just y alone, to construct a polynomial that approximates the derivatives and extrapolates into the next interval. Okay. So, what is the general method? Y n plus 1 plus h times some processor phi x n plus 1 x n plus 1, then the derivative terms okay. So, look at it, the value at n plus 1th stage demands values at n, n minus 1, n minus k plus 1, plus also it demands the derivative values at these points. Okay. So, this is a more general case, right. So, this can also be put it in a little different sense. As follows. So, this is function values at past points plus h. So, explicitly I am writing the phi okay. So, which can be written as so, here I is 1 to k and here we are including 0 as well. So, for the derivative. Okay. So, this is a more general method. So, once we write such a general method, few remarks. Okay. If B 0 is 0, okay, example, if B 0 is 0, example y n plus 1 a 1 y n plus a 2 y n minus 1 plus b 1 y n prime. If B 0, that is this B 0. So, look at it, what is B 0? B 0 is coefficient of y n plus 1 prime, and we are trying to compute y n plus 1. Now, what is y n plus 1 prime? X n plus 1. So, it demands y n plus 1, that means to compute y n plus 1, right hand side demands y n plus 1. Okay. So, now if B 0 is 0, then the right hand side does not demand y n plus 1. So, to compute y n plus 1, y n n minus 1 n minus k plus 1, and since B 0 is 0, we need from y n prime up to y n prime n minus k plus 1. So, that means, if you know the past values n to n minus k plus 1, one can compute y n plus 1. Hence, this method is explicit method. This method is explicit method. Okay. Now, if B 0 is non-zero, okay, say example y n plus 1 is say some 4 y n minus 6 y n plus 1 plus 2 h y n plus 1 prime plus 7 h. So, look at that, we are computing y n plus 1 and right hand side demands y n plus 1, because to compute y n plus 1 prime we need y n plus 1. So, that means this is implicit method. Why? Because right hand side, see, you are computing y n plus 1, but right hand side also demands y n plus 1. So, therefore, this is implicit method. Okay. So, let us try to discuss explicit methods. Okay. So, let us start explicit methods and try to understand. Okay. So, explicit methods. So, consider our initial value problem with okay. Now, integrating between one interval, that is x n to x n plus 1, we get okay. So, what we have done? We have integrated between just one interval. Okay. So, the method is, suppose this is x n. So, x n minus 1 n minus k plus 1. So, the method we are talking about explicit methods, that means to compute y here. So, we would like to compute y there, we need the past points y, okay, x n minus 1, x n minus k plus 1, right. So, now for that what we are doing, we are just integrating between only one step. Okay. Now, where are we trying to use the past points? Okay. So, the past points, look at this. So, now we have to approximate f by a suitable polynomial. Okay. So, here we will use the past points. Okay. So, what we do to evaluate 2, one can approximate f of x y by a polynomial that interpolates f of x y at k points. What are they? X n y n, x n minus 1 y n minus 1, x n minus k. Okay. So, look, so we have to evaluate this integrand, the integration. So, one can approximate f by a polynomial that interpolates f at k points, and what are they? X n, x n minus 1, x n minus k. So, these are all past points. So, there is nothing implicit, everything is explicit. Okay. So, now how do we approximate? Okay. Well, you can use forward or backward difference formulas, right. So, let us try to use one of them to approximate f. Okay. So, we use Newton's backward difference formula, okay, of, well, if there are k pass points, what would be the degree of the polynomial that could be approximated? K minus 1. Okay. Now, in order to use this, we have to assume that if f has k constant derivatives, our polynomial of degree k minus 1 will be f n plus x minus x n by h delta f n x minus x n x minus x n minus 1 factorial to h squared, then the second order differences, okay, plus x minus x n minus 1 n minus k plus 2, this is k minus 1 term, h power k minus 1 and this. Okay. So, this is backward operator, where this is backward operator. Okay. So, that is this on f n is backward operator. Okay. So, now plus k factorial and this is the remainder term. Okay. So, this where f k is the kth derivative of f evaluated at some zeta in the interval okay. So, look at it, we have used Newton's backward difference formula and this is given by f n plus x minus x n by h. This is the first difference, second order differences, higher order differences, and this is the k minus 1 term, and then kth term is the remainder term that involves derivatives of f, kth order derivative of f. Okay. So, now our task is to simplify further and substitute this in the integrand. Okay. So, before we substitute, let us try to simplify this further. So, note that you have, see, p k minus 1 is a function of x, right. So, you have these variables x minus x n, your variable is now here x, that is x minus x n, x minus x n minus 1, so on and so forth. So, we try to introduce a change of variable as follows. Okay. So, what is the change of variable? Changing the variable in 3 by u equals to x minus x n by h. Okay. Look at that. So, you have backward Newton's difference formula, Newton's backward difference formula. So, this is x minus x n by h, we are transforming it to new variable u, and hence we try to convert everything in terms of u. Okay. So, if note that if this is u, what will be x minus x n minus 1? Okay. What will be that? Let us see, this is, that means u h, okay, plus x n is x. Okay. So, we need a next term is x minus h. So, we need to compute this. Okay. So, what will be this with this notation? Okay. So, this will be u plus 1. Okay. So, you can verify. So, hence with this our polynomial become p k minus 1 x n plus u h, because x is this, equals f n, it is approximate, u times first difference. So, what could be the next term? Again we go back. See, this is x minus x n by h is u. So, x minus x n by h is 1 u. Now, we have x minus x n minus 1 by h. So, that must be u plus 1. Okay. So, u plus 1 by 2 factorial second order differences. Okay. Now, the next term, u plus k minus 1 k minus 1 factorial, k minus 1 factorial, this will be k minus 2, because we need one previous term. So, u plus 1, u plus 2, u plus k minus 2, k minus 1 factorial, k minus 1 f n plus the next term k factorial, okay, into h power k okay. Look, what did we do? We have transformed this using a variable u. Okay. So, correspondingly one h goes to x minus x n by h, another h goes to this, but if you observe there is no h here in this term in the denominator. So, therefore, we have to supply 1 h 2 and n minus k plus 1 okay, for this term. So, that means total how many k. So, accordingly we get in numerator h power k and in the denominator h power k. So, the denominator got adjusted into u plus 1, u plus 2 this, and in the numerator it remained. Okay. Right. So, now further this can be simplified as follows. P k minus 1 x n plus. So, what is our new variable now? It is u is our new variable. So, this is equals m 0 to k minus 1 minus 1 power m minus u m plus u c k h power k okay. So, we have to define where u minus u c m is okay. So, what we have done? We have approximated and we have put it in a simpler form, and this is the remainder term. Okay. Now, what is our concern? Our concern was to substitute the polynomial that has been approximated into this integrand, which was our 2. Okay. So, we have approximated f by using k past points, and that was 4. Okay. So, now what we are supposed to do? Now, using 4 into with this notation, dx will be h du. Okay. This is because of the change of the variable. Okay. So, now when we substitute this in the integrand, the expression 2 reduces as follows. Okay. Plus h 0 to 1 So, I will explain why this is 0 to 1. This is a remainder term and the variable is du. So, why the our limits x n to x n plus 1, okay. But what was our transformation? Our transformation was x equals to x n plus u h. Okay. So, therefore, when x is x n, u is varying from 0, and when x is x n plus 1. So, this will be when x is x n, this implies u is 0, and when x is x n plus 1, x n plus 1 minus x n is h. So, this is okay. So, the change of variables brings this limits. Okay. So, now this is equals plus h. I take the integrand inside, summation outside, which is permitted. So, 0 k minus 1. So, some new notation So, I have introduced a new notation. Look, this same thing I am writing where this has got in. So, integral has gone inside and the differences I have retained as it is, and this is definitely T k. So, that means, when the summation has come out, what is left? Integral 0 to 1 minus 1 power m and minus u c m. So, that must be this. So, therefore, let us define where. So, these are some kind of quotes equals this. Okay. So, where this and this h, because h power k and there is one h power k plus 1 . So, this is the remainder. Okay. Right. So, try to follow carefully. So, y x n plus 1 is, we have approximated the integrand by polynomial using k pass points, and we got a polynomial of degree k minus 1, and that has been substituted in the integrand. Okay. So, that has been substituted and then we got a simplified form, and these are the quotes. Okay. So, now let us simplify further. So, the approximation is given by So, after removing the error, I have removed the error term and then using this approximation. So, this is our formula. However, these quotes are to be computed. Okay. Right. So, then the next issue is calculating these quotes. Okay. So, let us, so m 0. Okay. So, m 0 because what was our formula? Our formula was and minus UCM was also defined. Okay. So, using that, this will be 1 . Okay. Okay. So, you can compute and to realize that it is this. So, now these quotes will be computed to get the formula. Okay. So, on doing that we get the formula. So, therefore, because what was our formula? 1 0 and 0 difference, that is f n, okay, and 1 0 is just 1 0, gamma 1 0 is just 1. So, therefore, first term should be f n. Okay. So, then sorry gamma 0 0. So, then gamma 1 0 is half. So, therefore, the next term should be half del f n, right. Okay. So, half f n 5 by 12, the second order differences 3 by 8. Okay. So, this is the general formula. Okay. Now, why did we say this is explicit? Look, to compute y n plus 1 we need past points, okay, because you see this is a backward difference. So, it will ask for n minus 1, so on. Okay. So, now let us come to specific. So, this is more general. So, let us try to fix up the number of points. Okay. K is 3, okay, and past points x n, y n, x n minus 1, y n minus 1, x n minus 2. So, suppose these are the past points. Okay. That means, we are approximating by a polynomial, okay, using these past points. So, we have 3 points, therefore, we expect a quadratic, and that quadratic has been integrated to get the formula. So, in this case y n plus 1 is y n plus h So, we have only 3 points. So, we get differences up to second order plus there must be an error, right, and what is the error? T k is if k is 3, h power 4, and this must be evaluated as a reminder. So, I can write h power 4. Okay. So, now we have to expand. So, first order difference has been backward operator has been expanded. Okay. So, this is plus okay. So, we got the approximation and which is explicit and which is multi-step. Why multi-step? To compute y n plus 1 we need n minus 1 n minus 2. Okay. So, let us write down this explicitly. So, this is the error. Okay. So, this is an explicit method which is third order. Why? The error is h power 4. So, the order of the method is 1 less. So, that is third order and this has specific name in literature Adams-Bashforth method. Okay. So, this is called Adams-Bashforth method. Okay. Now, naturally the next question comes, can we reduce the error? Okay. So, what is a see here we have derived a multi-step method and it is a third order method. What did we do? We have used past points and how many? 3 past points. So, we have approximated by a quadratic. So, now the natural question arises, can we improve upon this method? Yeah. So, what is the idea? Instead of 3 past points, if we use more past points, then we get a better polynomial and then that will be extrapolated, right. So, let us try with 4 points. Okay. Yeah. So, now if we try for 4 points, okay. So, k equals 4 and the points are okay. So, now I am not explaining the derivation, because all that we have to do is simply take our general expression, and since we have 1, 2, 3, 4 points, then we can compute the differences up to third order. Okay. So, by doing so we get, already we have done the quotes up to third order, right. So, we get the following formula. Okay. Okay. So, this on simplification (55 f n), 59 f n minus 1. Coefficients are very big. So, computation will be little tedious. Okay. And the error Okay. So, this is another method. So, this is Adams-Bashforth method. Okay. If we use more points, we get the corresponding. Look at that, the coefficients are completely different. Okay. So, you keep on using more pass points and then you will get different methods. Okay. So, let us quickly look at some problem, so that we get some idea. So, this is a VP, compute y of 0.6 using Bashforth. Okay. So, let us say the formula is given. Okay. What are we asking? To compute y of 0.6, right. What was our x 0 0, x 1, x 2, x 3. So, essentially we are asking to compute y 3, right. Now, to compute y 3, your Adams-Bashforth is asking some past points, right, y 1, y 2, y 0 of course. Okay. See, let us look at your method, Adams-Bashforth. Okay. So, y 3, y 2, f 3, f 2, sorry, f 2, because n is 2, f 1, 5 f 0. Okay. So, to compute f 1 and f 2, we need y 1 and y 2, right. So, remark, need y 0 of course, y 1, y 2 to compute f 0, f 1, f 2. So, we have y 0. So, there is no issue with this, but who will give us f 1 and f 2? Okay. So, in the question itself, it should have been mentioned whatever the past values required, compute using something. Using which kind of method? Of course, using an explicit method, then only we can compute. Okay. So, let us say it is mentioned compute the past points, say using Euler's method. Okay. So, let us compute using Euler method. Okay. So, y dashed was so x 0 is 0, y 0 is minus 1. Okay. So, therefore, y 1 is so y 0 is minus 1, h is 0.2, minus 2 x 0 is 0, so this is okay. then y 2 h times minus 2 x 1, okay, then minus okay. So, this is minus 0.72. So, we got y 1 y 2 using Euler method. That means, we have all the data, we have y 0, y 1, y 2. So, now what was our of course, we need immediately f 0. So, f 0 is minus 1, f 0 is minus of minus 1. So, this is 1, okay. Then f 1 is minus 2 x 1 minus y 1, okay. So, f 1 is 0.4 and f 2 is minus 0.08. So, we have to compute. Then y 3, which is y of 0.6, this is given by y 2 plus h by 12 23 f 2 minus 16 f 1 plus 5 f 0. So, this is h is f 2 minus 16 f 1 plus 5. So, we get approximate value which is minus 1.224. Okay. So, what we have done, we need the past values. Okay. So, to compute using Adams-Bashforth, we need 3 past values n, n minus 1, n minus 2, and in the question it should be given using which method one should compute the past values. Okay. So, in the present problem we have used Euler's method, the simple, but if you really need a better accuracy, one should use maybe higher order Taylor series method or RK method. Okay. So, that will give more accurate results. Okay. So, you have seen what is the logic. We have integrated between one interval and then the polynomial has been fitted with using k past points. Okay. So, now the larger the value of k, the better approximation for the polynomial, and hence the error will be less. So, we have tried k 3 and then k 4, and k 3 there is a specific name Adams-Bashforth, which is an explicit method, and k 4 also is an explicit method. Suppose instead of that, if the right hand side demands y n plus 1 as well. So, then we end up with something called implicit method. Okay. So, we try to discuss in the next class. Okay. So, these methods. Thank you. Have a nice day.